Hello, everyone. Welcome back to CPE 517-WS Digital and Computer System Architecture. This is lecture 10, part 1, multi-core processors. First, some logistics. Some of the slides are from David Patterson's class, Howie and Sen Nipsky. All the credits goes to the original authors and all the errors are mine. We do some reordering and modifications due to our own requirement. So one recap slide from last, I think, 2 slides ago, right? So last lecture is about data log parallelism. We talked about vectorized architecture, SIMD extension, and GPU. That's one way of solving these problems in ILP limitation. Another way is simultaneous multi-threading. If you still remember this slide, what we talk about is that in reservation station or in superscala, we see that we have multiple instruction fetch, instruction decoding, executor, write back, memory loader, etc., etc. We say we already have many hardware supports mechanisms that can support multiple threads. Okay, and that includes a large set of virtual register, and we also provide register naming for different threads, and we do out of order execution for different execution streams. So in order to support multi-threading, we only have to add per thread renaming table and keep separate pieces for different threads to keep track of their own status and moving on independently, right? Okay, so in order to do that, this is the hardware we actually have today. It's one of the hardware I open box for my own desktop and show you guys here. A little bit of illustration here. We see there are 2 dies, right? 2 sockets of CPUs or processors. Probably one processor is quad core. So we have 4 cores on each CPU. In total, we have 2 sockets. And then inside of each socket, we have 4 cores. Okay. And then we also see that close to these CPUs, we see DIMMs, right? The memory interface to plug in the DRAM, right? So while you also see that potentially these 2 are closer, well, these 2 are closer to the bottom socket. So this is the motherboard that we're gonna be focused upon for memory and CPU, right? It's actually called NUMA architecture, non-uniform memory access. Basically, when the socket from this socket, the thread from this socket access either this memory or this memory, they have to go through the processor, IPC, and then from IPC to the DRAMs, right? Similarly, from here to the remote memory. So we say this is non-uniform memory access. We're gonna talk about this later. Okay, so then come back from the hardware, come back to the needs. Why we do that? The reason is because we have a lot of data-intensive applications, and data-intensive somehow by default implies that different data probably can be processed independently, and we have the growing interest in server performance. That's why we have data centers and cloud computing providers like Amazon, Microsoft Azure, and then Google Cloud, other different cloud providers. They are interested in server performance. And then increasing desktop performance becomes less important. Why? Because everything when you are doing, you typically use this desktop as an interface, and then you log into the servers to do the real job. So we really care about the server performance, and the desktop is more like just an interface, okay? Or laptops, similarly. So improving the desktop performance becomes less important. So that's why we have to go to multi-core or even scaling to more powerful processors and servers. People also have improved understanding how to use multiprocessor effectively, right? So I still remember when I was undergrad, for multiprocessor at that moment in early 2000, I think multiprocessor is very, very rare, at least in my undergrad age. We typically do single core. But when it goes to, when I was doing my PhD, I think at that moment is the prosperity of the SSD and the multi-core. So typically people gonna use CPUs quad-core, dual-core, core-socket, core, or even more cores at that moment. And today is even many-core CPU, like 100-core, 20-core CPU, or many-core definitely GPU, or other like accelerators, which comes with a lot of cores. The reason by doing this, people is embracing even like your phone, right? So your phone is also multi-core, like 8 core, 16 cores. So it's almost like I would say everywhere, right? Prevalence. It's everywhere that using multi-core. So people are forced or they born to know what is multi-core. It's the same like a network. I remember when I was in undergrad in my dorm, we don't have wireless communications, like wireless networks. We typically do wired network. But today in Stevens, I don't think anyone uses wired network anymore. Well, very few of you guys use wired network, right? So that's the progress of the terminology and understanding of concepts. People being adapted, they've been getting used to this kind of new technologies. So that's why it's easier for people to accept the multiprocessor right now. And also, multiprocessor is easy, right? So, for example, if you want to improve the performance further by increasing the performance of a single unicore processor, it's pretty hard. It's not hard. It's not easy to replicate. And improving them is really even harder, right? So for multi-core, I know there's consistency or coherence issues, which we're going to talk about this lecture, but it's relatively simpler and easier to invest and get replicated. Right? Okay, so when it goes to multi-core, then we have no choice but go through this kind of terminologies, Flyn's taxonomy, okay? So we're going to talk about 3 of them, mostly because these 3 are like a point commercial product, right? So for uniprocessor, like single instruction, single data, it's like serial execution. Like I only have a single core, so definitely have single instruction and also single data being executed. And then we have single instruction, multiple data, SIMD. This is what we've been discussed. We've been discussing last lecture, right? Like GPU, SIMD extension, vectorized architecture. Then MIMD is what we're going to cover today's lecture, this lecture, lecture 10, and next lecture, lecture 11, okay? What we say is you have multiple cores and different cores are executing different instructions and working on different data, okay? I'm not saying MISD, like multiple instructions on single data is not likely. It's likely, but I would say it's possible, not likely. It's possible, but very rare. Okay, so focusing upon the difference of SIMD and MIMD. SIMD means you use a single instruction to execute different data, right? So that's what I mentioned before, you vectorize the addition, matrix multiplication. For different data, you do the same instruction. That's what we call it by single instruction multiple data. And when it goes to multiple instruction multiple data, it's like we have our today's multi-core CPU. Different cores has their own PCs, has their own instruction fetch, has their own entire pipeline. So they can execute different instructions on different data. Right? MIMD is popular because it's flexibility, right? So it allows n programs on n data. Well, it also implies that it's more complicated comparing to SIMD because SIMD only have to execute a single instruction on multiple data. So at least the fetching the instruction, dissolving the dependencies are relatively easier. Okay, so back to basics. There are two ways of doing multi-core, computation. First, the motivation is that a parallel computer is a collection of processing elements like workers that cooperate, communicate to solve a large problem or large problems faster. So parallel architecture is equal to a parallel computer architecture plus communication architecture, like networking, right? There are two popular classes of multiprocessors with respect to memory. First is centralized memory multiprocessor. So when it goes to centralized memory processor, it means all of those memories goes like the same, like uniform to all the processors. And second is physically distributed memory processor. Different memories are attached to different processors. You have local and remote memory, right? So you might be curious, okay, hey, professor, we're talking about multiprocessor computing. Why are we concerned about memory? The reason is like this. When we do computation, you remember one instruction contains what? Op, code, and what? Operand, right? So what is opcode? Opcode is the instruction operation, right? What is the operand? Operand is data. So one CPU only have its cache like tens of megabytes. It definitely cannot hold even typical data, like your photo is like 30 megabytes or even larger. So one cache typically cannot hold the data. So that's why we have to go to memory, because memory is second tier of the memory storage for us to provide the operand, right? So that's why when we talk about multiprocessor, we talk about memory. And since we have multiprocessors and processors attached to different, DIMMs, right? DRAMs. So how do we distribute these operands to which like execution unit? It's very important. That's why we discuss memory. Okay. So these are two ways we discussed before. You have like centralized memory, which means all the processors have their own cache. Okay, this is cache. It's even the symbol is like a cache, but it's really meaning is the memory, right? Physical memory, it's cache. Well, so centralized memory means all the processors have uniform access to all the memories, okay? All the memories are the same distance to them, to each processor. This is a typical example is GPU, okay? And then the distributed memory can be factorized into two cases. First is on the same machine, different dies, like what we mentioned here. This, right? This is distributed memory. So you have two sockets, and then they're on the same motherboard. There could also be, they are different machines, okay? You need to use Ethernet to communicate. But in this case, we focus upon the NUMA architecture that is on the same motherboard still. Just the different processes are attached of their own local memories. Well, they can also access remote memory, but it has to go through the processor and then go to the memory. Okay. So this is what we talked about just now, NUMA, right? So what we do is we have every CPU has their own attached local memory, every one of them. And then for communicating, like for this CPU to access data from here, it has to go through the CPU that is local to this memory, and then request the data, and then the data has to reply back to this CPU. Right? We call this non-uniform memory architecture. This is very popular. It's today. It's right now, all your computers, if you have multi-socket, it's like a NUMA. So centralized multiprocessor is what we mentioned about, right? Uniform, what we call it, SMPs. It's good in terms of what the memories are the same for what is processors. This requires large caches because single memory can satisfy memory demand of a small number of processors. If we want to have a lot of processors who want to access the memory, then it's gonna be like congested, right? It can only scale to a few thousand processors by using a switch and many memory banks because different ones have to go to those banks to access the data. Although scaling beyond this is technically conceivable, it becomes less attractive as the number of processors sharing the centralized memory increases due to the congestion introduced. For distributed memory processor, it is cost effective to scale memory bandwidth because typically, okay, I would say majority of the case applications, they actually access the local memory, right? So that's why we have NUMA. It means for the local processor, I would say 99% of the time they access the local memory. That's very miracle, right? But it's the truth because single attached DRAM could be like tens or hundreds of gigabytes. So it's almost always certainly that local processors has their own data to access and the capacity to hold the data as well. It reduces the latency of local memory access because it's local and memory traffic is relatively low, right? But the cons is you have to communicate between processors in order to provide the remote access. We also have to change the software so that we know this is NUMA architecture. That's why you see a lot of NUMA architecture operating system, NUMA architecture VM, NUMA architecture machine learning, NUMA architecture like data analytics. I actually did a lot of work on this kind of research before. Okay, so last slide for this part. So typically to communicate across processors, we can use MPI, message passing interface. It's a very popular paradigm for inter-process communication through Ethernet. You can also use mmap, which is another way. Based communication, but it has to be on the same machine. For MPI, because it's through Ethernet, it can go across processors. Okay, MPI is on the same machine, but it's supporting NUMA and the cross-process communication, right? Cross-process. When you communicate across shared memory address, right? So you typically use, right, this is NUMA, okay? So for distributed case, it's NUMA. Sorry, for distributed, it has to go through network, so it's MPI. But for NUMA and unified memory access, you can use mmap for cross-process communication and OpenMP, which you're going to discuss in the part 6 of this lecture. OpenMP for cross-thread, okay? Cross-thread communication. So both of them, I think, are very useful. If you can get a taste about MPI and OpenMP through this class, it's really good. I encourage you guys to get it, okay? I think this is it for this part.